Hi there, my name is Vlad, and I'd like to share with you some of the exciting features and improvements coming to the VFX Graph. In this session, we will cover some of the more prominent ones, go over examples how they're used, and discuss how they lead to better and more robust artist workflows. First, here's a quick summary of what we will cover in this presentation. The new output events, which enable you to synchronize the spawning of VFX particles with other elements in your scene. Mesh LODs. Effects using mesh outputs can now be optimized with the implementation of a level of detail system, which allows you to specify simpler meshes for distant particles. The added multi-mesh support increases further the variety you can get from your mesh outputs. Particles can now pick from up to 4 different meshes to be rendered with. We'll also have a quick chat about the new documentation available on VFX Graph contexts, operators, and blocks. Mesh sampling enables VFX artists to read mesh data and, among other things, position particles directly on meshes. The same functionality is also available for skinned mesh renderers, and we will cover how to spawn particles on an animating character. We will quickly cover how to exclude your particles from temporal anti-aliasing to reduce unwanted ghosting. The VFX Graph has now also better integration with the universal render pipeline, including the addition of lit outputs for URP, as well as support for the URP 2D renderer. We will also cover the new helpers that assist you in specifying the correct bounds for your effects so they would display properly. The new graphics buffer support allows you to send large amounts of data from C# to your visual effect, and we'll look at a couple of examples. The addition of a signed distance field Baker tool directly in Unity, allowing you to create SDFs to drive the simulation of your effects without leaving the engine. And last but not least, the powerful refactor of the shader graph integration into the visual effect graph, which gives you access to all the materials and material types of the high-definition render pipeline. That's a lot of ground to cover, so let's get started. First, we'll take a look at what you can already expect in the latest Unity 2020 release. Output events are really useful when you want the initial spawning of your particles to drive something else in your scene. For example, creating lights, playing sounds, or interacting with your gameplay logic. They enable you to synchronize the spawning of particles with other elements on your level by sending an event which can be received in your C# script. Here we have a spawner context which spawns particles at random intervals. These then trigger the spawning of a nested system which contains the spark effect playing in the scene. If we select our visual effect in the hierarchy, we can see that it has a helper script which is looking for an output event with the name Flash, which it will use to spawn a light prefab. Further down, there's another script looking for the same output event to spawn a sound. All that is left for us to do is create a new output event, call it Flash, and this will synchronize the spawning of lights and sounds from both scripts with the random sparks in our effect. Output events also allow you to obtain the initial attributes of new particles set in the spawner context. Here is a scene which I clearly put a lot of time and effort into making. We can see that the lights are inheriting the particle color as they push the PoreCube around. It's important to note that output events are used in conjunction with the spawner context. They cannot be used later in the graph to obtain attribute information for particles after they have been spawned. In this example, the green color can be obtained in C# through the output event, but the red color cannot be accessed as it is set after the output event has already triggered. The documentation has a C# example of how to use output events. The Visual Effect Graph package also contains a number of helper scripts to allow you to set up some of the most common interactions, like the ones we've just discussed, without having to write any code. You can download these from the package manager by going to Window, Package Manager, selecting the Visual Effect Graph package, and then under Samples, import the output event helpers. Next, we have the experimental multi-mesh and mesh level of detail features. Actually, let's rewind quickly and talk about experimental features for a second. Experimental features are features which are publicly released so we can get a feedback and improve on their UX. Because of this, they might still undergo some changes. To enable experimental features, go to the Preferences menu under Visual Effect and just enable the experimental operators and blocks. Right, back to the new mesh output features. When selected, particle mesh outputs now have in the inspector a new mesh count parameter, which enables you to specify up to 4 meshes per output directly in the VFX Graph window. There is also an LOD checkbox to determine how you would like to treat those meshes. If you enable the checkbox, the output will use the meshes you've specified to progressively reduce the complexity of your particle geometry the further they get from the camera. This allows you to render significantly more particles as they will be pushing less geometry. In this example, we're simulating over 1 million mesh particles. At the most detailed level, the rocks have over 1300 vertices, so without the LOD system, we would be processing over 1 billion vertices. With this feature, however, we're able to drastically reduce that number without compromising on the visual quality. For each LOD you are using, you can specify at what ratio it would be visible. A value of 10, for example, means that the mesh needs to occupy at least 10% of the screen to be selected. The LOD values correspond to the meshes you've specified above. Radius scale can be used to adjust the radius of the bounding sphere used in the LOD calculations for each particle. You can adjust this value to affect in unison all of the LOD values you've specified above till you get the desired look. The other side of this feature is to simply use the multiple meshes to add variety. Here we have a level populated with particle meshes. We're using 4 meshes and are letting the output randomly pick one for each particle. By adding some random rotation, we can quickly populate the level in a believable way. You can query which mesh has been selected by reading the particle mesh index attribute. If your meshes are using different textures, you can also pack all the textures together in a flipbook or a texture 2D array, enable the flipbook UV mode, and then use the mesh index attribute to set the text index attribute, which is usually used for picking a texture index. We have also added the first iteration of mesh sampling operators, which allow you to spawn particles directly on meshes. This feature has been extended further in Unity 2021.1, so stay tuned and we're going to come back to this in a second with more details. It's also worth mentioning that we have improved the documentation for the VFX Graph. This includes various tooltips throughout the tool itself, as well as a library of operators and blocks, code examples, and visuals. All of these are accessible in the VFX Graph manual online. Next, let's take a look at some features and improvements which landed in Unity 2021.1. As promised, we will cover here in more detail the mesh sampling improvements, as well as the addition of the skin mesh sampling. Mesh sampling allows you to obtain data from meshes and use it within the VFX Graph. The most common use case, of course, is spawning particles directly on a mesh without having to worry about baking it first into a point cache. Let's take a look at mesh sampling in practice. Here we have a scene with a mesh and a simple visual effect which is just rendering a lot of particles on the same spot. We will instead make these particles spawn on the shape of this mesh. First important bit before setting up mesh or skin mesh sampling is to ensure that the mesh we want to read data from has read-write enabled. You can set this up in the import settings of your mesh. Select your mesh, turn on read-write, scroll down, and press apply. Then we simply add a position mesh block and assign our shape. You can see that our particles don't align with the mesh in the scene. That's because our transform values are different from the ones belonging to the mesh transform. To alleviate this, we can simply nest our visual effect within the mesh and reset its transform. By default, particles are placed on the mesh vertices. We can, however, choose placement alongside the edges or the surface of the mesh. Surface mode also has more advanced options for using uniform or barycentric surface coordinates, allowing you to manually control the particle positioning on the surface of the mesh. The current setup will work as long as our system is in local space. Sometimes, however, we may want to spawn particles in world space, for example, if we don't want our effect to be nested within the mesh transform. In this case, we need to transform the position of the particles to match the transform of the mesh in the world. To do so, we will first expose a transform property in Blackboard, which we will then use to link the mesh transform to. This transform property should be set in world space, as we will be receiving the world space values of the mesh transform. We will then link it to our transform position operator. Then we can use a property binder script, which already ships with the VFX Graph, to link the transform property which is created with the transform of our mesh in the scene. If you make sure that all your positions are set to world space, then the particles will correctly conform to the mesh regardless where it is. Since we're setting the position in initialize, particles will inherit the shape position only once when they spawn, and after this they will remain in place, leaving a trail behind as you move the mesh. If we want them to always conform to the mesh shape, we can simply move the transformation to the output so it will be applied each frame. You can also sample meshes and skin mesh renderers directly with a sample operator. This allows you to access more data beyond just the position we've been using so far. In this example, we are still using the position to spawn particles on the mesh. Then we're using the normals to animate them away from the mesh. Then we're using both the normals and the tangents on the mesh to orient our particles so they face away from the mesh, giving them a look of peeling away from it. And finally, we use the UVs to sample the same texture the mesh is using and apply the value to the particle color. This creates a more unified look for the effect by making particles inherit the color of the mesh area they're spawning from. Skinned mesh sampling is quite similar to regular mesh sampling, with the exception that you need the skin mesh renderer you're using to be actually present in your scene. As with regular mesh sampling, we have to make sure that the mesh we're trying to sample from has read-write enabled. To create a link, we will expose a skin mesh renderer in Blackboard and assign our character from the scene to it. Then, we can create a position skin mesh block in initialize and link our exposed skin mesh renderer to it. If we enter play mode, however, we will see that the particles are not following the character. To remedy this, we can do the same thing we did with the mesh sampling example. We'll expose a transform, and then with the binder script we will link this transform with the transform of our skinned mesh. In a typical setup, you may want to link your particles to the root hip bone of your character, but the exact bone can be different depending on the setup of your rig. We'll set up the new position, connect the exposed transform to the transform position operator, and make sure that both it and our system are using world space. Now, if we enter play mode, the particles will correctly spawn and trail behind. If we would like for the particles to stick to the character, we can move the position blocks to our output. This wraps up mesh and skin mesh sampling. If your project is using temporal anti-aliasing, you may discover that your smaller particles can receive some blurriness or ghosting. And let's face it, no one wants to be ghosted. To give artists more control, we have added the option to exclude transparent particles from TAA. Disabling TAA is especially useful for small particles like dust or embers, which might otherwise get smeared or lost when using TAA. Here's a quick comparison. And finally, let's go over what you can expect in the next major visual effects release coming at the end of this year in Unity 2021.2. Since this release is still being worked on, some of the items we will cover here might undergo additional changes. This is also not an exhaustive list, as we have more already completed, as well as some work in progress which we're hoping to include in the release. Let's start first with the highly requested lit particle support for the universal render pipeline. The workflow in URP is very similar to the one in HDRP, and lit outputs are available for planar primitives, so things like quads and triangles, as well as for meshes and particle strips. We have also renamed the HDRP outputs accordingly, so you can now have a project set up with both pipelines using an URP and an HDRP lit output, and the visual effect graph will just pick the one which corresponds to your currently assigned and active render pipeline. We have also enabled the visual effects graph to run on the URP 2D renderer. In this setup here, we have some visual effects rain added to the level. In the first pass of the support, we have enabled the visual effects graph to use both sorting layers and order in layer, so it can sort between different visual effects in your scene, as well as between a visual effect and the sprites in your level. A common challenge for artists starting with the visual effects graph is figuring out why their effects disappear. This can sometimes happen when the bounds are smaller than the effect itself, so when the camera no longer sees the bounds, it will clip the visual effect even if some of its particles should still be visible. However, manually setting bounds is not always reliable, as your effect might have random values, which might play different each time. An additional challenge is if you have many systems within your effect, then tweaking them all separately doesn't scale well. To address this, we have added some helpers to the bound system. The bounds now have three options. Manual is the classic behavior of user-supplied values we have had so far. In this mode, the responsibility for specifying the correct bounds rests on you. When using automatic, for a small performance cost, your bounds will constantly update to ensure they always encompass your effect. This is very useful when prototyping, but it is not as efficient as the other modes when shipping a final product. And last but not least, Recorded allows you to play the effect for a while to calculate the maximum bounds it would need. This is the most optimal choice, and as such, it is good practice to record proper close bounds once you've finished working on your effect. To record the bounds, you need to have an instance of your currently open effect in the scene. The record option itself is available in the Target Game Object window. If your effect is not already attached to this window, you can select it in the hierarchy and then click Attach. Once you are all set up, you can press Record. Let the effect play until you feel it has undergone most of its changes and the bounds are not constantly changing anymore. Then click Apply Bounds to transfer these new values to the current bounds of your system. It is important to note that the bounds computations don't consider any changes in your output. Changes in certain attributes such as the position, scale, or pivot of your particles in your outputs might actually make your particles step outside of the bounds. To alleviate that, you can add some padding to your bounds in the initialize context here. Graphics buffer support is a slightly more technical addition to our next release, but one with a huge impact. This feature makes it easier to transfer large amounts of data from C# to your visual effect. Previously, for scenarios such as this, if you wanted to track multiple positions, you had to rely on baking the position data to textures. With the addition of graphics buffer support, you can fetch and sample structured buffers, which opens the doors to a whole new level of interacting with your graph via script. Fair warning, the next example contains a giant spider-like creature. I tried to make the legs more wobbly for anyone with arachnophobia, but it's a fine line between a spider and an octopus. In this scenario, we are simply raycasting in a radius around the effect to get all colliders within range. The hit point of each collider is then sent over to the visual effects graph using a graphics buffer. This data is constantly updated as the spider moves around, allowing its legs to completely procedurally interact with the level. Also new to Unity this year is the addition of a sign distance field Baker tool. This enables artists to create SDFs for use in the visual effects graph directly within Unity without the need to go to any external programs. SDFs are useful for a range of cases, such as simulating collisions with more complex objects or for making particles conform to custom shapes. The tool can be accessed through Window, Visual Effects, Utilities, SDF Bake Tool. Let's take a look at how to use the tool. On top here, you can specify the texture resolution for the SDF. You should try to keep this value low and only increase it if you need more precision. The tool allows you to bake both single meshes or prefabs containing one or more meshes into an SDF file. To use the tool, first assign the desired asset. We can simply press Bake and preview the result. The tool preview offers a volume, slice, and SDF visualization mode. The bounds of the bake can also be adjusted on top. You can use the box center and desired box size to select only part of your asset to bake. A use case for this would be if you have a car mesh, for example, but only need information about the front part of it and would like to use up the full SDF resolution for it. Live Update allows you to continuously bake the SDF and see the updated values in real time. This option is only available at lower to mid resolutions, as it can be performance heavy. You can also access some additional settings from this menu. These are used for fine-tuning your baking for more problematic or complex meshes and resolve the distinction between the inside and outside areas of your mesh. When you're happy with the result, just click Save SDF and save your asset. You can also save the tool settings themselves in case you would like to come back and reuse the same setup. There are many use cases for SDFs within the VFX Graph, like assigning position, creating a traction, or colliding with the asset. As a quick demonstration, we can open our effect, create a position sign distance field block, and assign a new SDF. We have also refactored the visual effect shader graph integration for the high-definition render pipeline. This adds a lot of new creative functionality, such as the ability to create vertex animation for your particles, as well as the power to use the full range of HDRP shader graph materials in the VFX Graph. This includes also more exotic ones like hair and fabric. Here is how to use it. We're going to create a new HDRP shader graph asset. Let's open it and dock the window next to our visual effects window. The only thing needed to make it work with the visual effects graph is to tick the Support VFX Graph checkbox. When this is done, we can save our shader graph and assign it directly to our visual effect output. This already gives us full access to the HDRP shader with different materials and material types. Once you set up your shader graph and save it, you can select your output and in the inspector create material overrides just like you would with regular materials. You can still access the usual visual effects specific settings below. It's important to note that you no longer have to specify a visual effect active target. The visual effect graph now uses the HDRP active target, which means that the same shader graph can be used for both particles and for other objects in your scene. To illustrate this further, here we're creating a new material from the shader used with our visual effects soap bubbles. Then we assign this material to a regular sphere in the scene, and it just works. The new shader graph integration will be on by default. If you're not ready to switch right away, you can opt out of it by disabling it in the visual effect preferences. We're of course also planning on bringing the same refactor for the universal render pipeline soon. This concludes the session on the next stage of development for the visual effect graph. This was just a slice of what's new, and we're still working diligently on delivering a more polished and powerful tool into your hands for this year's release. You can already try out many of the new features we discussed by downloading the latest public beta of Unity 2021.2. Thank you so much for listening, I hope you enjoyed the session, and our team really looks forward to seeing all the incredible things that you will create.